What am I doing? I got this keyboard back when Overwatch was released. And when's the last time I touched the numpad? I'm no accountant. Ooh, this could work. But man, whenever I use a keyboard too long, my wrists are in so much pain. I wonder if I could, now this I like. Well, isn't it a bit thick? And do I really need all these keys? Let's see, how did Hulk do it again? Sweet Liberty! What do we have here? Just enough keys to keep my fingers from jumping around, capable of split wireless usage so I don't have to worry about cables or wrist pain, and it is thin! I could slide this thing in my pocket. Maybe not if it transforms like that.
Is this thing an Autobot?
Even is
How do I get one of these?
Is this case 3D
I can see
printed?
through the keycaps.
Saying you can just build this? How does something like this even work?
If you somehow haven't already guessed it, today we're building a keyboard, but not just any keyboard. No. We're building a 36 key, split, ortholinear, column staggered, mechanical keyboard as thin as my phone. If you didn't get all that, don't worry, I'll explain in a bit. You see, this is the first keyboard I've ever built from scratch, and it also happens to be the most versatile and sleek keyboard I've ever used. So if you're interested in seeing all the cool things throughout the video and all the shortfalls I had, which is gonna be wrapping up in a version 2, then be sure to stick around. But for now, let's go over the main plan for Butterfly V1. Inspired by the popular Chalkify keyboard, I want to create something using a similar layout that features the new Kale ultra-thin butterfly switches, also known as the PG1316Ss. In other words, I want to make an upgraded Chalkify board that uses butterfly switches, hence the name Butterfly. The board's going to be ortholinear and column staggered. And to best understand what that means, first let's think of a normal keyboard. It has a bunch of these rows that are slightly offset or staggered from each other, which was historically done to benefit typewriter mechanisms so that the lever components wouldn't intersect. However, for some reason in this digital age, we're still producing the majority of keyboards the same exact way. Now, to understand why that's so crazy to me, I want you to take a look at your hand. Pick a finger and try to move it diagonally, left and right, forward and backward. Now move that same finger just forward and backward. It's much easier, right? So let's straighten up those staggered rows and make the keys ortholinear. Next, I want you to open up your hand and picture a line between your fingertips. If you didn't accidentally cut them down to be the same size in some sort of freak accident, they're probably all different lengths and not in a straight line. So let's take those columns and stagger them a bit to better fit the natural shape of your hand. To push the envelope even further, when you're typing on a normal keyboard, pay attention to your wrists and your overall posture. The chances are your wrists are either twisted like a contortion artist or your shoulders are in quite an uncomfortable position. We can actually fix this by splitting the keyboard in half and moving each side apart into the most natural resting positions for your hands. And for some extra credit on top of all that, we're going to be instilling Butterfly with the ability to tent. All that means is we're going to have the ability to twist the keyboard so that our forearm bones are not overlapping each other while we're typing, which is more comfortable for some people and less comfortable for others. Just the options there if you want it. Enough with the ergonomics though. As far as components go, we're gonna need a PCB, those butterfly switches we talked about, a diode for each switch, and some fitting keycaps. I may have already tried printing some keycaps for these switches, but the precision wasn't exactly there, so we're gonna be using these really cool transparent ones instead. And beyond that, since we're aiming for a wireless board, we're gonna need to squeeze some batteries on both halves. Something like these 250 milliamp hour LiPos should do the trick. Additionally, we'll be using ZMK, which is a popular firmware utility for custom wireless boards that can even handle things like layer swapping. Remember, we're only working with 36 keys here, which means switching between layers allows us to interact with our numbers, our symbols, and even some of our modifiers. You may think that sounds annoying at first, but while we'll need to press or hold an additional button to switch between different layers, we can minimize any large movements we need to make with each finger. Ultimately, this will keep them closer to the home row for more comfort and speed down the line compared to a normal size keyboard. For microcontrollers, we're gonna be using a pair of Nice Nano V2s, and we might even toss on these awesome Nice View screens for things like battery visibility, connection and layer status, and maybe even to show me my words per minute. Ideally, I'll enclose it all in a sleek, 3D printed, low profile case, and also include quality of life things like a power switch and a reset button that the original Chalkify didn't have. Now, I think it's finally time to get to the build. We're gonna start it out by hopping into KiCad to design my first ever PCB. Well, actually, we're gonna dive into YouTube for about an hour or so to first become experts on PCB design. Okay. Maybe not an expert, but at least good enough to be dangerous. I started out in the schematic editor where we can tell our program exactly what components we have and how they should connect. To that end, I added all 18 switches on this half of the keyboard, along with a diode for each, which will simply allow electricity to flow in a single direction. And then I added the Nice Nano V2, the screen, power switch, reset button, and connected everything together. The most important thing to note here is the matrix type structure that all the keys are connected in. Given there's not enough pins to directly assign to each individual key, we can set the board up as a system system of rows and columns, where an entire row goes to just one pin, and the same for an entire column. Then we can identify which key is pressed depending on which row and column that key is in. And after I was happy with all the pin assignments, I moved into the PCB editor, where we can actually physically place each footprint on the board. A footprint is basically the interface between the component and the PCB. So for example, the footprint of this butterfly key switch is composed of 4 mounting pads for structural integrity all around the corners, and 2 through-hole mounting points for the 2 electrical contacts on the bottom of the switch. Now, this switch is supposed to be what we call surface mounted, meaning you put down some solder paste, put the component on top of it, and then melt that solder using something like a hot plate or oven. This will flow the solder that was in the paste and make a good electrical connection. However, I don't currently have a way to do this short of tossing some sand in the pan and heating it up, or trying to get really precise with a heat gun. So I decided to commit what feels like a cardinal sin and try mounting these surface mount switches by flowing solder through these through holes. I did a few test connections on this board that I also bought along with the switches, and everything seemed to work all right. By switching this meter into continuity mode, we can hear a beep every time I press down this key, meaning the connection is being made. The other thing I was able to quickly test and am super happy with is the diodes I chose. I picked up these cute little guys to pair with each switch, and they're just small enough to rest inside the LED cutout below the switches, meaning I can hide them away out of sight and keep them from taking up any valuable space. Anyway, back to the PCB. After I positioned all the keys in that Shopify-like layout that I'm aiming for, I tossed in all the pads for the diodes, positioned the footprints for the microcontroller, power switch, reset button, and screen. I also made sure there was enough space next to the pinky cluster right here for the battery to fit in before drawing my edge cuts. Now these are a bit of a pain to draw out in KiCad, but if you have your spacing right in the project settings and give it a little bit of time, it's not too bad. This solid line will simply tell the manufacturer where we want the edge of our PCB to be. And finally, it was time to wire everything up, which was one of the most enjoyable and effortless parts of the design thus far. Since we already defined where we wanted all of our connections to be in the previous page, once I clicked on a connection point, the program automatically told me where I needed to route the copper runs. So you just have to make sure to avoid placing any routes too close to the edge and add in any vias to go above or below other routes, keeping them from overlapping. Lastly, I ran a final check on the board to make sure there's nothing seriously wrong with it, and it was at this moment that I realized I had only finished one of the sides. A while later, and another side completed, I added something called fill layers for better electrical performance, exported both sides as Gerber files, and sent them off to a manufacturer. There are a ton of manufacturers out there to choose from, but I went with JLC PCB. I uploaded all my files with mostly default options selected and got the PCBs back in just a few days. And that brings us to today's sponsor. Just kidding. Oh, and I found out how to add my own silkscreen, so I put this S tier meme on the back. Now to encase these bad boys. While the PCBs were being shipped to me, I was actually able to start designing the case by exporting the KiCad project as an object file and importing them directly into Fusion 360. My goal is to make the case as minimal as possible while still balancing in some sort of support and also a bit of protection. However, I soon learned that I didn't plan properly enough before putting in my order for the PCBs. You see, I have some lofty goals. I want to make this keyboard super thin while still being capable of tenting. I want it to be split and wireless, but link up into a single piece for situations like working on your lap where it will be annoying to have them independent. And I also want those linked halves to fold up into some sort of self-containing cocoon to travel safely. I think it may be possible, but I forgot to add mounting holes in the PCB to screw into the case. And because I'm using through holes, there's going to be exposed traces on the bottom of the PCB. All that to say, I'm going to have to find some sort of creative way to clamp the board in place since there's no other non-permanent way to secure it to the case. And I'm also going to need to place something on the bottom of the PCB to cover up those exposed traces so there's no false triggers on the switches. Anyway, for now, I'm going to leave those lofty dreams for Butterfly V2 and instead just focus on making this the best keyboard I can at the time. That also stands as a good testing point for version 1. That means I'm going to give up on it being the absolute most thin keyboard I've ever seen by mounting the tenting solution, which are these cheap yet robust phone stands, on a piece of acrylic that's also going to act as the base of the case and cover up those traces. The top part of the case, which will help secure the board, will be 3D printed using this neat looking yellow PETG that sticks with the butterfly theme and provides enough strength even in those thinner parts of the profile, like around the USB-C input and the power switch. It took more than a couple iterations to dial in the overall shape to make sure the profile didn't get in the way of typing, and it was also easily printable. I also made sure to extend out this little section below where the microcontroller and screen will go that with sufficient amount of applied force will allow the user to press the reset button just by flexing the plastic a little bit. Lastly, I added some tiny screw holes to aid in clamping down the acrylic panel and sent the design over to my printer. I'm also going to make a temporary travel case to lock in both halves of the keyboard with some Velcro and keep all the components safe using some cleverly placed plastic standoffs. Let's get this thing assembled. The process turned out to be quite therapeutic. I'd simply lay down a bit of solder paste, carefully put the component down, and then use the fine tip on the iron to flow the solder. I did the same exact thing with these tiny power switches and reset buttons. Then I cut down these standoffs, allowing the microcontroller to mount flat against the PCB, and I soldered it into place. After that, I cut down the wires connected to the battery and stripped the ends so I could connect them to their associated pads. Next up, it was time for the switches. I applied some good old flux to encourage capillary flow and then melted solder down through the holes, making sure to just add enough to make a solid electrical connection without adding so much that it mounds up and makes an uneven surface. I also put a bit of solder down on 2 of the mounting pads to make sure the switch stayed in place, but I added a bit too much on some of them and a few keycaps ended up sticking later due to the tiny tolerances they have around this switch. And if you don't have some good tweezers in just the right angle, they are super annoying to pop off. I ended up having to perform some surgery on a couple of them because I would mess up the scissor type hinge mechanism that makes these switches tick, or click, I guess. However, I can't argue with the fact that they are very satisfying to pop on. And lastly, it's time for the screen. It sits at the perfect height, just on top of those black plastic pieces left over from the pins holding the nice nano in place. Unfortunately though, that also makes it the tallest part of our board. So I did make sure to raise these edges on the case to protect it. However, in the next version, I have an idea of how to get the screens to sit below the keycaps, even while still being mounted on top of the microcontroller. So if you're interested in seeing how I save a huge couple millimeters, make sure to stick around. After taking just a few more whiffs of solder fumes, it was finally time to try powering them up. One side good, the other side? Well, here comes another thing to fix. I guess one of the power lanes was just barely close enough to the edge to be cut off in the manufacturing process. So for now, I just bridged the gap from this positive line that runs through the power switch to the appropriate pin on the microcontroller. Now let's get that case on. Now you might be wondering, how do we get these cool paperweights to become fully functioning keyboards? Well, I'm not going to go over the process in depth because there's a ton of good guides out there already, and there's nothing specifically special about this Butterfly ZMK build. But to make a long story very, very short, each half of the keyboard, left and right, requires its own firmware build. So we can configure the key maps and settings for each side. Again, everything is fully addressable, and this is where we can decide what keys we want on what layer and where. Once everything's error-free and compiled, we can toss each firmware build onto each of the corresponding boards by tossing them into a bootloader mode. And after flashing, the halves should hopefully be able to communicate wirelessly and also with any devices you pair. Now, as a quick note, I really like the screens, but for some reason, one of them was being quite spotty, so I'm gonna remove them and put them on the next version if they still seem worth it. We were able to get them to display all the things we wanted though, like the layer status and battery and even words per minute. But even without them, this thing is pretty freaking cool. I think this thing looks sick, and I enjoyed typing on it, which is the most important thing. I need your help though. I've referenced the next version of this board more than a few times throughout the video, and if you have any additional ideas that you think I should check out, let me know what they are. For now, here's a quick list of changes that I want to make. Of course, I need to fix any routing issues like the power lane being cut off. I want to widen the tolerance around the battery and also find a better way to secure it. Along those same lines, I'm thinking about adding a standardized connector for the battery for any user who wants to swap or replace it easily. And this time, I better not forget to include those screw holes in the PCB for mounting to the case. I find that the case is currently nice and functional, but I want to achieve those lofty goals I mentioned earlier, so I am already prototyping an awesome solution for that. And there are a few concepts I want to explore, but I'm not yet entirely sold on. So that about wraps up the video. If you actually made it this far, go ahead and like and subscribe for me. And if you just skipped here, what the heck, you can still like and subscribe. Keep creating, and I'll catch you in the next one.